In this week's video for Calc 3, we're going to talk about limits, and so right now in this video we're just going to develop the idea of a limit, and it's something that we've seen before in Calc 1. So we saw problems like this before, so if we just take a moment and solve each of these, the first one we can actually do using the direct substitution property. We might remember, since it's continuous, we're able to just plug it in and we get 3 times 1 minus 2, or just 1. And then the second type of problem, we notice that, well, there's an asymptote at x is equal to 2, right? Vertical asymptote. And so what we have to do is look at the left and right hand limits. Well, if I look at the left hand limit, so if I approach 2 from the left, and just for notation, I'm going to call that f, I get minus infinity. And then if I look at the right hand limit, so again, that's 2 plus of f, I get positive infinity. So what I end up saying overall is that this limit does not exist. That was kind of our idea of when a limit exists. In our last example, if I look at the arctangent function as x goes to infinity, we could look at this graphically, tabularly, or whatnot, and what we would get is that it's just pi over 2. Okay. So that's just some brief reminders of limits. And so conceptually, when we were thinking of a limit in Calc 1, we said a limit exists if and only if the left hand limit is equal to the right hand limit. And so just graphically, what we would say is that, okay, well, if we have, okay, here's a function, let's think about a point A, and there's my function value, and maybe my curve looks something like this. What I should be able to see is that as I come in from either side, the limit value is the same. Again, I don't actually need the point to exist. I could have that as an open circle and the function up here, but still the limit would exist. I just need the curve to match the same thing on both sides. When we go into Calc 3, the idea is exactly the same. Okay, and so what we say is that for kind of at least our intuitive understanding of a limit is that the limit exists if and only if the limit is the same along, and here's a new phrase, along all paths approaching that point. Again, we're thinking of that point as a vector. They have to exist and are equal. Okay, well, you might imagine that there's a kind of a tricky part with this definition, right? It's that all paths have to exist and be equal. Well, how in the world do we check all paths, right? We could have, okay, let's just do a couple examples. Okay, well, here are 3 series of points. Well, I could look at it simply from the left, the right, and the top and bottom, whatever those are in 3-dimensional space, right? I could look at all different sets of those. Okay, well, that's finite, maybe, but it still takes a while. But if I start considering kind of diagonal paths or curvy paths, right? I could even do some bizarre, maze type path in here. And I'd have to look along this path, right? I could also consider a spiral path. Okay. I would have to literally look along all paths. And so how do we employ this definition in actually finding the value of a limit? Well, there's actually maybe an easier solution. If I think about the negation, and the negation is just that if we get 2 different limits along 2 paths to this point A, then the limit as we approach A of f does not exist. And that is going to be a little bit easier for us to use going forward. So in the next video, we'll actually go through a few different examples related to this and see how to do this mathematically.